All right.
And no one's going to.
All right, so we're kind of hitting 11.3 and 11.4 again. Just some applications with the dot and the cross product. So let's remember what we'd said about work. We've talked about work a little bit. We did some nice lifting problems and pumping problems before, and those will show up again before too long. So we said work done by a constant force acting along the direction so we have a constant force from point P to Q. We said that the work was the magnitude of the force times the distance that we travel. So if our force is acting in the direction of travel, we just multiply the magnitude of the force times the distance that it travels, and that's our work. So I'm going to say W here, WE. If F is not acting in the direction of motion, then we will draw a nice picture so you can see what we're talking about. So we have a situation that looks something like this. So here's F, and here's the direction of motion. So this is our vector, our force vector here, and this is point P, and this is point Q here at the end of the vector. And the angle between these is theta. Well, the component of the force in the direction of motion, we can break it into two pieces. This magnitude is the magnitude of F times the cosine of theta. So we just take the magnitude of the force in the direction of motion times the distance that we move. So the work done is going to be given by the magnitude of F times the cosine of theta times the distance that this thing travels. And does this look like a familiar quantity here? This is F dot PQ. So our work is given by this dot product. And if we recognize that F, the magnitude of F times the cosine of theta, that is the magnitude of the projection of F onto PQ. And this is our notation for that, PQ, projection of F onto PQ. Oops, I need my vector sign here. So we can also write that the work is this magnitude of the projection, the vector projection, onto PQ of F times the length of PQ. So two different ways of thinking about work. This one is the most common, just F dot PQ. A pretty Very straightforward application of the dot product. One interesting thing that we'll do in second semester is calculate the work done if our force is acting along some arbitrary curve in space. So not necessarily in a straight line. If our path is on a curve, we calculate this work and we do what we call a line integral. And that's a lot of fun. All right, so questions on work. So let's do an easy example with work, and then we'll talk about torque. So we have a force given by (3i plus 4j plus 5k). And this force moves a particle from point P at 2, 1, 0 to point Q at 4, 6, 2. And we want the work done by the force. So nice easy application of the dot product. First we need our vector PQ. So what's PQ going to be here? What's our vector from P to Q? -2, -5? So we're subtracting 4 minus 2 is 2, 6 minus 1 is positive 5. There we go. And 2 minus 0 is 2. So there's PQ. And then our work is F dot PQ. So we're just going to make our dot product of these two vectors. And I'm just writing in our different notation here, just so we stay familiar with it. And this dot product is going to be, let's see, 6 plus 20 plus 10. So our work is 36. In international units, in the metric system, our units, and I think we talked about this before, units for work are Newton meters. Normally, Newton meter or joule. And we can also talk about Newton centimeters, those kinds of things. But our normal unit, most common unit is a Newton meter or a joule. In imperial units, our most common unit is a foot-pound. We could talk about inch-pounds and that kind of thing as well. What's that? Pound foot? Yeah, that's interesting that they say foot pounds rather than pound feet. So sometimes you'll hear pound feet, but I think it's more common to hear foot pounds. Especially if you're talking about, when you talk about torque, if you have a torque wrench, the mechanics will always talk about foot pounds. Such and such foot pounds of torque. But it's interesting that there's Newton meters in one system and pound feet. All right, questions? Okay, torque. Torque is a moment. Torque is the moment we're going to write it as a vector of F. Thank you. Is a moment of F about a point P. Do we remember what we said a moment was? How did we define a moment? What was special about moments? Nobody remembers? A moment is a quantity weighted by its distance from an axis. So we're talking about this we're giving this force some weight proportional to its distance from this point P. So we define our torque as a moment. So let's draw a picture here. And I want to let me undo that. And we're in 3 dimensions here. So this is point P, this is point Q, this is our force F, and this is our torque. And M tells us the tendency of PQ to rotate counterclockwise about the axis along M. And our magnitude of our torque, the magnitude of M, is the magnitude of PQ times the magnitude of F times the sine of theta. And theta is the angle between PQ and F. And this F sine theta is the component of F perpendicular to PQ. Let's draw another picture here. So if I have my force, we'll just draw it in the plane. So let's say this is PQ and this is F, like so. This would be theta. There's PQ. There's F. And this piece here, with this being a 90-degree angle, this is the magnitude of F times the sine of theta. So only the component of F perpendicular to PQ produces torque. So that's why we have this F sine theta. Only the component perpendicular to our motion, our vector here is going to cause it to rotate. Anything else is going to either cause it to try to move in one direction or the other direction. The force perpendicular is what causes it to rotate. So only this component produces torque. So questions on torque. And so our magnitude, we said our magnitude is PQ times the magnitude of PQ times F times sine theta. We find our torque vector, M, is PQ cross F. And our right hand rule applies. And the way you can think about torque is the torque points in the direction that a right-handed screw would travel as you turned it in that particular direction. So if the torque is going into the page, your screw would go into the page, and if the screw would come out of the page, then your torque is going out of the page. It's one way to think about torque. Right hand rule, righty tighty, lefty loosey. They're really the same thing. They're really the same thing. It's a cross product, so it's really the same thing. It helps me to think of the cross, like I said on Friday, think of the cross product as an action. The one vector is crossing onto the other vector, and the torque is, or the cross product is the direction that the screw would travel. That's what happens. That's what happens on tests where there's cross products and torque. Is people are doing this kind of thing. All right, so let's look at an example involving torque. So we're going to push a 3-foot horizontal bar with an upward force at a 70-degree angle to the bar. And we want the magnitude and the direction of the torque. So if we draw a picture here, here's our bar, and we're pushing our horizontal bar, and this is 3 feet long. And we're pushing upwards at a 70-degree angle. So our force, and did I say with an upward force, I didn't say the magnitude of the force, upward force of 20 pounds. So here's F, so we're pushing with 20 pounds, and this angle is 70 degrees. So we're saying that it's this component, this perpendicular component, that is causing this thing to rotate. All right, so our magnitude of our torque is just given by technical difficulties. This has never happened before. Let me do this. See if this helps. I'm just going to turn this off. Oh, I cut off my bar here, didn't I? There we go. So the magnitude of our torque is going to be the magnitude of PQ cross F. Sorry, that's not what I want to do. PQ cross F. There we go. So that's just going to be the length of PQ times the magnitude of F times the sine of theta. So that's just going to be 3 times 20 times the sine of 70 degrees. And when I multiply this out, this comes about out to 56.4 foot-pounds. And for this situation, if we apply our right-hand rule, so the direction, because these two are in the plane, our torque vector is going to be normal because it's a cross product. It's going to be normal to both PQ and F. So which direction is our torque going to be? Into or out of the page here? Davis says out. Out. So if we push, this thing is going to rotate this way, and if this were a screw, we'd be loosening the screw, lefty-loosey, so it would be out of the page. So if we pushed on this with this force, our rotation would tend to be counterclockwise, like so. And that would be our screw would go out of the page, returning it left. If we redraw this diagram, it might be easier to see. If I put PQ and F tail to tail, sometimes that can help. Here is PQ. And here is F. And this is our angle 70 degrees. So if we cross PQ onto F, if I think of that crossing PQ onto F, then our thumb is going to point out of the page. So we want, when I think of crossing these vectors, we're thinking of rotating PQ about its initial point. So to cross PQ onto F, I put them, it can help to put them tail to tail to visualize. If I cross PQ onto F, my thumb points out of the page here. So M would be pointing directly out of the screen, our torque vector. So questions on that example? I think the direction is what confuses most people when thinking about torque. So what direction would we push? How would we push relative to our bar to produce the maximum torque? Push at a 90-degree angle, right? We would push, so we'd be pushing directly this way. All right, one last little piece here, and then we're done for the day. We mentioned a couple of times the scalar triple product. And we said that the scalar triple product gave us the volume of a parallelepiped. And we said our scalar triple product was A dot B cross C. So this was a volume of kind of a little box, slanted box shape. And these three vectors, A, B, and C, are the adjacent sides. To calculate the volume of that box, to calculate this scalar triple product, we just find the determinant of the vector, or the matrix A1, A2, A3, B1, B2, B3, C1, C2, C3. So this is a nice, easy way to find the volume of a little box if we're given the sides in vectors. So I just, not that we're necessarily ever going to do anything with it. I just wanted you to have seen this and realize that this technique exists for finding the volume of this little thing. And we said that the magnitude of B cross C is the area of the parallelogram created with B and C as adjacent sides. So let me draw a little picture of this this parallelepiped. So if this is something like that, we drew this picture before, and if I turn this into a three-dimensional solid, I didn't do a very good job there. Let me redraw that. The bottom looks okay. My bottom's okay. Let me do the sides in a different color. I'll do the top in blue. So I just need to make this a little smaller. There we go, that looks a little better. So there's my parallelepiped. I'll do this side in green. There we go. So a slanted little box. And we need this back corner. I'll do this back corner in yellow. Like so. So that'd be the volume of this little box. And I mostly did that just so we could draw a little box. So that would give us the volume of that little thing. All right, questions? All right, so what we've done so far is we've kind of worked a little bit with the idea of the dot product, the cross product, vectors, that kind of thing. What we're going to do over the next couple of days is use vectors to talk about lines and planes in space. And vectors are going to be really our tool for dealing with these geometric shapes in 3 dimensions. So that's where we're headed with these vectors is to use them to describe surfaces in space, and then towards the end of the chapter we will talk about various kinds of 3-dimensional surfaces and how we visualize them and how we can represent them. So that's kind of where we're going in this chapter. And then in second semester, we'll start applying all of these tools to various 3-dimensional situations. All right. Homework. There you go.